If I asked you right now, like no calculator, to multiply a 114 by, say, 89, you would probably groan.
Oh, absolutely. I'd reach for my phone immediately.
Right. I mean, I know I would too. If you've ever tried to multiply large numbers in your head, you know it takes time.
Yeah, it takes a lot of mental energy.
And there are just uh, a lot of places to make a mistake. Well, it turns out hardware faces that exact same problem.
It really does, which is kind of counterintuitive.
Exactly. Inside the laptop you might be working on right now, or, the phone in your pocket, doing basic multiplication takes up massive physical space on the silicon chip.
Yeah, and it consumes a ton of power too.
It is this massive hidden bottleneck in the digital world.
We generally think of computers as these infinite, effortless math machines.
Right, like they just know the answer instantly.
Exactly. But down at the microscopic hardware level, multiplication is just incredibly expensive.
It's physical hardware doing the work.
Yeah. It's an engineering roadblock that designers have literally been battling for decades trying to shrink the physical footprint of these operations.
And that is exactly the focus of our source material today. We are looking at a highly technical presentation from 2026.
It's a really fascinating one, too.
Yeah, it's by an author named Lux036, and it's titled Optimized CSD Multiplier Synthesis and FIR Filter Applications.
I know, the title sounds incredibly
It
dense.
does sound like a mouthful.
But the core concept we are pulling from this is actually quite revolutionary for digital design.
The mission for this deep dive is to uncover a really specific hardware hack detailed in this presentation.
A hack that basically completely eradicates hardware multipliers.
Which is wild. We are going to look at how engineers are tricking computers into doing complex math without actually multiplying anything at all.
It's all about changing the representation.
Okay, let's unpack this. Why is hardware math so hard in the first place, and what is the alternative?
Well, to understand the alternative, we really have to look closely at the underlying problem with multiplication.
Like mechanically.
Right. If you have a standard multiplier taking an input of size n by another input of size n.
So let's say you are multiplying a 16-bit number by another 16-bit number.
Exactly. That hardware requires what computer scientists call order of n squared logic gates.
Order of n squared. So as the numbers get bigger, the hardware required just explodes exponentially.
Just gets huge fast.
Because a 16 by 16 grid means the hardware has to calculate, what, 256 individual partial products?
Yeah, 256. And that's before it even starts adding them all up.
Wow.
That is the root of the bottleneck right there. For a relatively small 16-bit input, where n equals 16, a standard hardware multiplier consumes over 200 logic gates.
And, 200 gates might not sound like a lot in a vacuum.
Right, but you have to consider the scale.
Yeah, when a device is trying to do millions of calculations a second, that physical real estate on the microchip becomes a problem.
A massive structural problem, not to mention the heat it generates and, the battery power it drains.
You can't just tell the computer to stop doing the math, obviously.
No, you still need the answers.
But you can change the method it uses to arrive at the answer. And that's utilizing what the source material calls a shift-add architecture.
Which is such an elegant solution.
The core insight here is that any integer constant can be decomposed into powers of 2.
Right.
Therefore, if you are multiplying a variable by a constant number, you actually don't need a physical multiplier circuit at all.
You really don't. You only need shifts, additions, and subtractions.
Let's walk through the physical mechanics of that.
Sure. So say you want the computer to multiply a variable, which we'll just call x, by a constant like 114.
X times 114.
You don't route that data to a multiplier. Instead, you break the number 114 down into its base components.
Because 114 is mathematically equal to 128 minus 16 plus 2.
Exactly. And the magic there is that those components are all specific powers of 2.
Right. 2 to the 7th power minus 2 to the 4th power plus 2 to the 1st power.
And in hardware design, multiplying by a power of 2 is essentially free.
Because it requires 0 logic gates, right?
0. You just physically shift the wires carrying the bits to the left.
It's literally just routing.
Yeah. So to multiply x by 114, the hardware simply calculates it as x shifted left by 7 minus x shifted left by 4 plus x shifted left by 1.
It's like paying for a $114 item in cash.
Oh, that's a good way to look at it.
Like instead of handing the cashier 114 individual $1 bills, which takes forever.
And is totally analogous to your standard tedious multiplier.
Right. Instead of that, you hand them a $128 bill, You take back a $16 bill in change, and then you hand over a $2 bill.
It's weird currency for sure.
Totally weird currency, but it gets you to the exact same total instantly.
What's fascinating here is how we choose those specific bills.
Or, in computer terms, the digit representation we use to encode those numbers.
Exactly. Normally, computers rely purely on standard binary.
Right, just ones and zeros.
Standard binary uses the digit set 0 and 1. The inherent flaw with standard binary, at least in this context, is that a string can have up to 50% non-zero digits.
And they often sit right next to each other consecutively.
Yes. Think about the number 15 in binary. It is written as 11101.
Meaning 4 physical adders have to be built just to process it.
Right. This presentation introduces a far more elegant representation called canonical signed digit, or CSD.
CSD basically expands the toolkit.
It really does.
Instead of restricting the system to just 0 and +1, CSD introduces a third option, -1.
Which is usually written simply as a minus sign.
And the presentation highlights a crucial defining rule for CSD. It never has consecutive non-zero digits.
Never. And that strict rule guarantees an incredibly sparse string of digits.
So you will never see a +1 right next to another +1 or a -1.
Nope. There's always at least one zero buffering them. Because of that mathematical guarantee, CSD drops the density of non-zero digits down to around 33%.
And that density metric is the whole ballgame.
It really is the key to the hardware savings.
Because every non-zero digit physically translates to an adder or a subtractor that has to be manufactured on the silicon.
Yeah, you have to physically build it.
So by mathematically ensuring the absolute minimal number of non-zero terms, CSD ensures the absolute minimal number of hardware adders required for synthesis.
To put that in perspective,
Yeah.
going back to our 16-bit example.
Right, where a standard multiplier took over 200 logic gates.
Exactly. By transitioning to the CSD shift-add architecture, that hardware requirement drops from 200 plus gates down to just 3 to 5 adders.
Wow, just 3 to 5.
It is a staggering level of optimization.
You are completely bypassing the most expensive piece of hardware on the chip.
Replacing it with a handful of cheap adders
Mhm.
and extracting the exact same mathematical precision.
But as with any major engineering shift, solving one problem immediately introduces a new constraint.
That is the golden rule of engineering.
Right. Once you rip out those massive multipliers and replace them with these CSD adders, you create a redundancy
I
problem.
needed to. Because CSD encoding is so strictly structured, ensuring those buffer zeros, it inevitably produces repeating patterns.
Across long strings of numbers.
Yeah. If a specific pattern, let's say +0 -0, shows up 3 separate times in a long calculation,
A standard flat logic generator isn't smart enough to recognize that repetition, is it?
not at all. It will just blindly read the string from left to right and physically instantiate 3 separate duplicate hardware adder networks.
Just to calculate the exact same mathematical pattern over and over again.
Right. You end up with an explosion of redundant adders crowding the chip.
Wait a second, though. I have to assume that constantly scanning strings to hunt down these repeating patterns takes processing power.
Oh, definitely.
So is it always worth the effort? Like, if the logic generator is hunting down tiny, insignificant patterns, wouldn't the cost of the optimization itself end up costing more than the hardware it supposedly saves?
That's a great point. And the designers of this system recognize that exact risk.
So how did they handle it?
They built in strict heuristics or rules of engagement to act as safety valves against over-optimization.
Okay, safety valves.
Yeah. For instance, the system actively aborts the optimization process if the pattern length is just 1.
Because there are 0 hardware savings to be found there.
Exactly. It also skips it if the pattern only occurs a single time.
That makes sense.
And crucially, it completely bypasses optimization if the number of non-zero digits, what the paper abbreviates as N and Z, is less than 2.
Okay, that NNZ cutoff makes complete structural sense.
Right.
Because a single non-zero digit is just a single term, and a single term cannot share logic.
Exactly. There has to be at least an addition or subtraction connecting 2 terms to create a physical logic structure that is actually worth sharing.
When those specific rules are met, however, and a valid, juicy pattern is identified, the system deploys an optimization technique.
Yes, it's called LCSRI.
And the mechanism behind LCSRI is brilliant.
It really is. It generates the physical shift-add hardware structure for that repeating pattern exactly once.
So that becomes the master structure.
Precisely. That's your master copy.
And for any subsequent occurrences of that pattern further down the CSD string, it doesn't build new adders.
Nope. It takes the output from the master structure and performs an arithmetic right shift.
In the code, this is represented by 3 greater than signs, right?
Yes. And the mechanics of that arithmetic right shift are vital here.
Because when you shift bits to the right to divide the master result, you risk changing the underlying math if you aren't careful with negative numbers.
Exactly. An arithmetic right shift specifically duplicates the most significant bit.
Which is the bit on the far left that acts as the sign indicator.
Right. By dragging that sign bit along as it shifts the numbers to the right, it preserves whether the number is positive or negative,
So the mathematical integrity stays perfectly intact.
while completely eliminating the redundant adder hardware.
The physical wire just routes the shared, correctly signed answer to the necessary bit position.
It's incredibly efficient.
Looking at the scale of these savings outlined in the source, it's really impressive. If you have a pattern like +0, -0, that repeats just twice.
This optimization drops the hardware requirement by 50%.
It goes from needing 4 adders to just 2 adders in one shift.
And as we established, that shift is basically free.
Right, and if you find a triple repeat, a pattern happening 3 times, the savings jump to a massive 67%.
You go from needing 6 separate adders down to just 2 adders and 2 shifts.
That is huge.
Yeah.
But optimizing a single string of math in a controlled environment is one thing.
Right. It's easy in a vacuum.
The real test is how this architecture scales to massive, complex digital devices that are doing thousands of different calculations simultaneously.
Well, the source material focuses this architecture on a very specific, ubiquitous real-world application.
Finite impulse response filters, or FIR filters.
Exactly. FIR filters are everywhere.
Yeah, if you are listening to this deep dive right now on a pair of noise-canceling headphones or connected to a modern Wi-Fi router, you are relying on FIR filters.
You use them every day. They're designed to compute weighted sums of delayed inputs.
Basically, taking a continuous stream of data, delaying it step by step, applying different weights or coefficients to different parts of the stream, and adding it all up to clean up the signal.
Right. But applying those varying weights requires constant, heavy multiplication.
Heavy multiplication.
A standard, high-quality 64-tap FIR filter requires 64 massive hardware multipliers operating in parallel.
Thousands of times a second.
Exactly.
And that massive power draw and sheer physical silicon area often prohibit engineers from scaling up these filters to be more accurate.
They just hit a physical wall.
But in these specific FIR filters, those mathematical weights are generally fixed. They are constant numbers.
And that's the breakthrough. By treating every single one of those 64 filter coefficients as a constant, we can apply our CSD logic.
Meaning every single one of those 64 massive multipliers is completely eradicated from the chip design.
The overarching hardware math requirement plummets from order of k times n squared down to just order of k times the average number of non-zero digits.
Which is a fraction of the cost, but the optimization doesn't stop at individual coefficients, does it?
No, it doesn't. If we connect this to the bigger picture, we reach the crown jewel of this entire architecture.
Cross-module CSE.
Yes. The single coefficient LCSR we just walked through only hunts for repetition within one isolated string of math.
Like within one specific coefficient.
Right. But cross-module CSE scales that concept up. It finds structural repetition across the entire filter bank of multiple, completely different coefficients.
So if coefficient A at the beginning of the filter has a specific subpattern, and coefficient D halfway down the filter happens to utilize that exact same sequence of additions and subtractions,
The system bridges them.
it builds the physical logic gates once and shares the answer across entirely different modules.
The presentation actually provides a specific mathematical formula to calculate the hardware savings of this cross-module sharing.
Which is the number of non-zero digits minus 1 multiplied by the occurrences minus 1.
Exactly.
Let's contextualize that formula based on the outline's claim. The presentation states that finding a 3 non-zero pattern occurring twice across different taps instantly saves 6 adders system-wide.
6 adders saved just from one tiny shared pattern.
The compounding effect of that across 64 taps is enormous.
The system impact is staggering. By bridging these multiple coefficients, cross-module CSE achieves an overarching system hardware reduction of 40 to 60%.
Whoa.
You are shrinking the core physical footprint of a major processing component by more than half.
With zero loss in mathematical accuracy.
Exactly.
Here's where it gets really interesting, because there is a perfect analogy for how this scales.
Okay, let's hear it.
It's exactly like meal prepping for the week.
Huh? I can see where this is going.
So, standard single-string LCSR is the equivalent of realizing you can chop all the onions you need for Tuesday's dinner right now, all at once.
Instead of chopping them individually as you cook 3 different dishes that night.
Right. It's smart, localized optimization.
Okay.
But cross-module CSE is realizing that every single dinner this week requires chopped onions.
So you batch chop a massive pile of onions on Sunday.
And distribute them or, shift them to entirely different recipes throughout the week.
It is a great visualization of cross-module sharing. However, the source notes a very strict technical requirement for that level of sharing.
Right. You have to prep those numbers the exact same way.
Yes. Specifically, narrower coefficients must be heavily padded with leading 0 characters.
That comes down to bit alignment, right?
Entirely.
If you have an 8-bit coefficient and a 12-bit coefficient, you can't just share logic blindly between them.
No, the math wouldn't work.
You have to pad the 8-bit one with leading zeros so that a specific bit position strictly encodes the exact same power of 2 across the entire module.
Right. If bit position 4 means 2 to the 4th in one module, it must structurally mean 2 to the 4th in all of them.
Because if the alignment is off, you're throwing chopped onions into a blender when you meant to put them in a frying pan.
Exactly. The alignment has to be absolutely mathematically rigid.
And moving from theoretical math to physical execution is where this presentation gets particularly grounding.
It really does. Because the author, Look036, didn't just theorize this 60% reduction.
They coded it into existence.
They built the algorithm into 2 completely separate programming paradigms.
A dual language architecture.
Yes. They implemented it in C++A using the C++14 standard, housed in an internal library called CSD CPP.
And they mirrored that implementation in Python using the Python 3.14 standard packaged as a C-sigit.
Translating complex hardware synthesis algorithms flawlessly across 2 distinct languages is notoriously difficult.
I can imagine.
This raises an important question about the rigorous quality assurance required for this level of optimization.
Right, because any tiny error gets multiplied across the whole system.
Exactly. And during development, they actually uncovered a critical silent failure in the original Python implementation.
They documented it as the first term sign bug.
Let's break down why that bug was so dangerous.
Okay.
We know that CSD strings use positive ones, zeros, and negative ones.
Right.
If a CSD string started with a negative term, for example, a string that looks like -0 minus "niece,"
The original Python parser was completely failing to register that leading minus sign.
it was silently dropping the negative designation on that very first term.
Wait, if it drops the initial minus sign, the math doesn't just get slightly inaccurate.
No, it completely inverts the foundation of the calculation.
Because instead of starting the sequence with -x, the hardware logic would instantiate a standard positive adder.
Starting the whole chain with positive x.
That's a huge problem.
It's a catastrophic arithmetic failure. Because this bug was operating silently in the background script that generates the hardware blueprints.
The resulting silicon chip would output complete garbage data, rendering the entire filter useless.
Precisely.
How is it structurally resolved?
The parser's fundamental logic was updated to actively interrogate the first term instantly upon reading a new string.
So before it does anything else.
Right. If it detects a minus sign in that leading position, it explicitly forces the instantiation of a subtractor.
Preserving that crucial leading negative value.
Exactly. And because they were running a dual language architecture, this fix had to be verified and deployed globally across both the CSD CPP and CSDigit libraries.
Finding a silent bug that destructive must have forced a massive overhaul of their testing protocols.
Oh, it prompted heavy verification sweeps.
I bet.
The presentation details that the C++ suite is now fortified with 54 dedicated tests.
And what about the Python suite?
The Python suite runs over 30 tests, but crucially, it utilizes hypothesis property checks.
Which is a really smart way to test. Hypothesis property checks throw massive amounts of randomized edge case data at the code to see if it breaks, rather than just testing the expected inputs.
Precisely. It ensures that the generated hardware code is perfectly deterministic and mathematically airtight.
No matter what weird string of CSD digits it encounters.
Exactly.
So what does this all mean?
It's a lot to take in.
It is.
Yeah.
We started this deep dive exploring a massive physical bottleneck in our daily devices, the exorbitant cost of hardware multipliers.
Right.
We broke down how decomposing numbers into canonical signed digit strings allows engineers to completely rip out those multipliers.
replacing them with simple, highly efficient shifts and adds.
We explored how the LCSR optimization prevents the system from blindly building duplicate adders.
By identifying and sharing repeating patterns within a single string.
And we saw how scaling that concept up through cross module CSE allows entirely different parts of a 64 tap FIR filter to share that same math.
Eradicating multipliers completely and shrinking the total adder hardware by up to 60%.
But we also saw through the first term sign bug that even the most brilliant, silicon saving architectural optimizations can be brought to the brink of failure by a single missing minus sign in a Python parser.
It is a sharp reminder of the intense precision demanded by digital design at this scale.
Definitely.
But stepping back from the code and the silicon, the underlying philosophy here is what I find most compelling.
How so?
We observed a strict physical constraint, the massive heat-generating, power-hungry reality of a hardware multiplier.
Yeah.
And we didn't solve it by waiting for a faster physical transistor or a new conductive material.
We solved it by entirely rethinking the mathematical representation of the data itself.
Exactly. Moving from standard binary to CSD made a physical hardware limit simply vanish.
It really is wild to think about.
It leaves you wondering, as we hit more walls in processing power and artificial intelligence, what other major, seemingly insurmountable computational roadblocks in our modern world aren't actually physical limits at all, but are just waiting for a clever shift in perspective?